Okay, so let's look at something called the Nernst equation. So the Nernst equation is a way to look at how much work or free energy does this electrochemical cell have the potential to do. So the Nernst equation says the maximum amount of work, remember work is in a unit of joules or kilojoules, a unit of energy, equals negative N Fe cell. So let's define all of this. So the maximum number of work, this is going to be in joules or kilojoules, some unit of energy. Negative N, N is the number of moles of electrons. F is called Faraday's constant. Faraday's constant is 96,485 coulombs per mole of electrons. And E cell is what's called the cell potential. And what the cell potential is it's the measure of the driving force of the cell reaction. It's measuring how much force this electrochemical cell has. The way we calculate E cell is E cell equals the oxidation potential plus the reduction potential. The oxidation potential and the reduction potential are things that you would look up in a textbook, or it would be given to you in a chart. So if we look and see if we can find some reduction potentials, usually the charts for reduction potentials are all given in reduction, and if you want to know what the oxidation potential is, you just change the sign. And the unit for the reduction and oxidation potentials are in volts. Let's see. I will give you the oxidation and reduction potentials for this example. Let's just see if I can find a chart, a table in your book. I will just tell you what they are for this example, and then if we ever were doing something like this on an exam, I would just give it to you. Let's see. Okay, so here in Appendix 6, this is the second edition of the textbook. If you have the first, second, or third edition of the textbook, all of those are fine. You might just have to look around for things. Might be a little different than what I see here in the second edition. So here are what's called standard reduction potentials, and here's a list of all the types of reduction reactions and what the standard, the E cell is for each of these in volts. So for example, we are going to do the example that we just looked at before, balancing the redox reaction. So we're going from aluminum to aluminum 3+, and then we're going from copper 2+ to copper. So from aluminum to aluminum 3+ is an oxidation reaction. Let's see if I can find that in here. Aluminum to aluminum 3+. So it's going to be different. I'm not going to find aluminum to aluminum 3 plus because that's an oxidation reaction, and these are reduction potentials. So what I'm going to find is the reduction potential. So the reduction potential from aluminum 3 to aluminum is negative 1.6. So if this is the reduction, I want the oxidation, so I'm going to change the sign. So here it says the standard reduction potential for aluminum 3 plus to aluminum is negative 1.66, but I want the oxidation potential, so it's going to be positive 1.66. And then I would look up the reduction potential, and it would be what it's shown in the chart because those are reduction potentials. So we'll use this formula from this example that we just did before. So let's write this out again. So I'm going to write out what the voltic cell notation is. Well, first, let's make up a question. Let's say we are going to use this Nernst equation to determine the maximum electrical work 1.00 grams of aluminum can obtain from the cell. And the voltic cell notation of what we're looking at is aluminum solid to aluminum 3 plus, copper 2 plus, aqueous to copper solid. So that's the voltic cell notation. So we are going to use this and the Nernst equation to calculate the maximum amount of work that 1 gram of aluminum can do. Okay, so I'm just going to see previous video for balanced equation. And we said the balanced equation was 2 moles of aluminum solid plus 3 moles of copper 2 plus aqueous produces 2 moles of aluminum 3 plus aqueous plus 3 moles of copper solid. So that's what we solved for in the previous video when we did an example balancing a redox reaction from voltic cell notation. So this is my balanced equation. So now let's use the Nernst equation to solve for the maximum amount of work. So I'm going to say maximum amount of work equals negative N. So what's N in this equation? It's the number of moles of electrons. Well, that's when you need to go back to your balanced equation and see how many moles of electrons were canceled. 6. So that means N equals 6. So 6 electrons times F, 96,485 coulombs per mole, 6 moles of electrons here, times E cell. Well, I don't know what E cell is first right now, so let's calculate that first. E cell, let's do that down here. So remember, E cell is the oxidation potential plus the reduction potential. So then you would go to a chart or a table that's provided. So again, I want the oxidation potential of aluminum to aluminum 3 plus. Again, there is no oxidation potential chart. What there is a reduction potential chart, and then I'm going to take the opposite sign of it because this is the number of volts of the reduction. So if I'm doing the oxidation, I want the opposite. So the oxidation potential of aluminum to aluminum 3 plus is going to be positive 1.66 volts plus the reduction potential of copper 2 to copper. So let's find copper 2 to copper somewhere in here. It's right here. Copper 2 to copper. Nope, that's copper 2 to copper 1. That's not what we want. You're going to make sure that you're using the right example. Copper 2 to copper is 0.34 volts. I don't need to change the sign here because that is the reduction potential. Plus 0.34 volts. Well, 1.666 plus 0.34 is 2.00 volts. That is my E cell. That's what I'm going to put here. 2.00 volts. So, moles will cancel, and a volt is a joules per coulomb. Volt is a joules per coulomb. So when you solve for this, you get these volts, the joules per coulomb. The coulomb will cancel, and you're going to be left with joules, which is why the maximum amount of work is going to be in a unit of joules when you use a unit of volts. So maximum work equals -6 times 96,485 times 2. Maximum work is, and remember this is in negative 1.12 times 10 to the 6th joules. And reporting it in joules is fine unless the question is asking for kilojoules. Either joules or kilojoules is fine. If you're solving it as is, it has to be in joules because the unit of a volt is a joules per coulomb. So this is the maximum amount of work that this reaction can undergo. But that's not what the question asks. The question says, how much work can 1 gram of aluminum do? Well, this balanced chemical equation is for 2 moles of aluminum. So 2 moles of aluminum produces this much work, and this sign is negative, meaning that this is a spontaneous reaction, because remember, at constant pressure, maximum amount of work equals delta G, which is Gibbs free energy. So you also could see this Nernst equation as delta G equals negative NF E cell. And delta G just tells you, is this reaction spontaneous or not? Remember, a negative number, a number that's less than 0, means this reaction is spontaneous, so it will produce energy. So this is a production of energy, these electrons flowing through this galvanic cell. So when you're doing the calculation, just keep in mind what this negative sign means. It's telling you the direction of the energy. It's telling you that this reaction is spontaneous. So let's convert. This is the amount of work that 2 moles of aluminum can do. So this amount of work per 2 moles of aluminum. So we need to do some dimensional analysis. You could do this however you want. The way that I would do it is I would say -1.12 times 10 to the 6th joules per 2 moles of aluminum. 1 mole of aluminum from the periodic table tells me is 26.98 grams. Moles of aluminum will cancel, and my answer is going to be -2.15 times 10 to the 4th joules of energy for 1 gram of aluminum. So this question kind of encompasses a lot of what we've talked about in this chapter. You can definitely expect to see something like this on the exam. You'll do this in your lab dealing with electrochemistry. Things to pay attention to here is that N is the number of moles of electrons from the balanced equation. So that's where my 6 electrons came for. I had to see how many electrons are being transferred. That's the number of electrons that we're canceling out. That's why N is 6. Also pay attention to the number of, well, not the number, but when you look up the oxidation potential, you're going to be looking it up in a chart called the reduction potential chart. So you're going to need to change the sign from in this case, it was negative to positive. So you could add these together and get the number of volts. And remember that a volt is a joules per coulomb, which is why your unit is going to be in joules, because moles will cancel and coulombs will cancel, and you're going to be left with joules. So this is an example of a Nernst equation. It's a way to quantify the amount of work or the free energy of an electrochemical cell. So you could either do the maximum amount of work, or you could calculate the free energy of a reaction. And then think about what that means thermodynamically. This is a spontaneous reaction, which makes sense. Batteries produce energy. You would expect it to have a negative delta G. So this is the Nernst equation used to solve for the amount of work that an electrochemical cell can obtain.